5, 4, 3, 2, 1.
Charlie Marcus, definitely.
Right on time. Now, I think this has to come on. You're doing that back there? La la la. Okay. Yep. There is another route to topological superconductivity that comes to us through the fractional quantum Hall effect. And it's the Majorana states that live in the cores of vortices. And it was inspired by, in particular, another kind of, if you want to say, P-wave superconductor or spinless or spin-polarized superconducting state, the 5/2 fractional quantum Hall state, the unique even denominator fractional state with a box around it right here, that was explained theoretically by Reed and Green in this famous paper. Again, you see I'm taking pictures from Jason Alisea for helping me explain it, but from this famous paper. So really, I don't know whether it's literally a coincidence, but the timing of the origin of the wire-based ideas in around 2000, 2001, which I started my presentation with from Kitaev, and this analysis by Reed and Green, and I'll just read you from their paper. To conclude, our main results are P-wave pairing in spinless or spin-polarized fermions, that was the 5/2 state, in the weak pairing phase, leads to the properties also found in the fractional quantum Hall effect in the more Reed states, and supports the idea of non-abelian statistics as a robust property, at least in the case of a pure system. Such statistics will also occur for the vortices in such P-wave states in general in charged superfluids. And then it points out, by the way, that this was already understood earlier as occurring in the zero modes of vortex core of the A phase of superfluid helium-3, all the way back to the early 90s. So Reed and Green introduced the idea of the vortices in the 5/2 fractional quantum Hall state, when you deviate slightly from the exact filling factor, that those vortices will contain this picture is supposed to indicate that the braid statistics force you to cross a line cut, which gives you this factor of 1/2 when you bring this guy around that one or that around that one. Someone has to pass through the line cut. But roughly, if you ignore that for a second, this tells you that this vortex core contains a Majorana. That's where this story came from. And that was Ivanoff, and this paper really laid that out for this problem. But this has become its own industry of looking in the core of vortices and superconductors. Here from this paper from Gia and co-workers, of a 3D topological insulator on top of a conventional S-wave superconductor. And here, looking at the core of a vortex, here you see a zero bias peak, interpreted in this case as a Majorana zero mode, living in the core of that vortex. Now, I'm not going to spend any time at all. I'm just trying to paint as a background that there was another route more or less going on in parallel where vortices in P-wave superconductors, or in these extended systems of topological insulators and superconductors, were another place where superconductivity gave rise to Majoranas. I do want to say that if you go back much earlier now to the 1990s, you'll find already people were scanning. This is kind of early days of scanning tunneling microscopes. Harold Hess was already scanning over a vortex in a superconductor and finding peaks in the conductance of a scanning tunneling tip. But in this particular case, has nothing to do with Majoranas. This is simply that there's a normal metal core in the middle of a vortex. That is, it's an uncondensed state. And as we discussed earlier, tunneling into a superconductor with a normal electron is kind of tough. But tunneling into a metal is easy. So the peak associated with this, with this case where you're sitting in the middle of the vortex, having this peak, is really because you're tunneling into a normal metal, not because you're tunneling into a anything having to do with a discrete zero bias state. And in fact, there's even papers in the literature now from 2011 in which, depending on parameters of the system, this three-dimensional vortex can either be metallic-like or it can cross through a transition and be Majorana-like. So now the vortex, depending on the parameters of the model, in this case they're tuning the chemical potential, will go through a topological transition and make this transition from a metallic core of a vortex to a topological core of a vortex, depending on parameters of the system. And so it's not obvious which one is which. But this has become a means of identifying in various systems. Here is the iron-based superconductors. You zoom in on a vortex core, and you can see as you move off center that in the middle of the core it starts to look like the kind of Majorana data that we've been looking at before. But now it's an entirely different physical system. Now it's moving along in the core of a vortex and seeing this now what really looks like a discrete state. It doesn't look like a big fat blur. It really looks like some discrete object sitting in the middle. But again, it's the same kind of thinking, which is that if you can tunnel in to a discrete state in the middle of a vortex, that it will show up as a zero energy state midway between the gap of the superconductor surrounding it, and implying, at least in this paper, that this is evidence of a Majorana bound state living in that vortex core. Okay, good. So far, so good. Now what I want to do is try to hybridize the two ideas that we've talked about so far, namely that you can make a nanowire and put a Zeeman field and a magnetic field or ferromagnetic insulator and spin orbit coupling and superconductivity and spin orbit coupling and large G factor and create Majoranas at the ends, or you can make a vortex. And so now what I would like to do is put those two together. And the key piece of physics that I want to put them together with is something called the Little Parks effect. The Little Parks effect was first recognized by Bill Little and his student, I think, Parks. And this was in 1962. And this was the first very simple, there were more complicated ways earlier, but this was the first simple demonstration that the quantum of flux was h over 2e, or hc over 2e, depending on here, they use units of hc over 2e. That is, it was evidence for the pairing. And remember, this is only a few years after BCS. So the idea that there should be 2 as the effective charge of the Cooper pair was first demonstrated by seeing this so-called Little Parks effect. The Little Parks effect was just that the critical temperature of a superconductor that was in the shape of a cylinder oscillates as a function of the applied magnetic field. So this is the superconducting state, this is the normal state, this is the applied magnetic field in units of the flux quantum, and here the key discovery was that there was that 2 in the denominator. That was not known before this and a few other papers that were going on at the same time. And this modulation of the transition temperature that had to do with fluxoid quantization around the cylindrical superconductor was what the evidence was here. And this was, how they measured off of the oscilloscope. Now, if I fast forward about 50 years, or 40 years, something interesting happened to the Little Parks effect, and it was really studied in only a very few papers, that as the cylinder got smaller and smaller, and here they are using this insulated quartz filament with either aluminum or gold indium surrounding, evaporated on this insulating quartz cylinder, an interesting thing happened to the Little Parks effect, which is that the transition temperature, when you were at the half integer quantization, would all of a sudden, this would go all the way from the superconducting state, it would be driven normal even at the lowest temperatures. So instead of being a small modulation of the transition temperature, in this case, the system simply didn't superconduct at all, down to the lowest temperatures that they could measure. And so here is the superconducting state, but when they got to a half a flux quantum, the system became normal. And this was called, and the theory of this had been worked out, it was called the destructive Little Parks effect, because it had completely destroyed superconductivity. So here's superconductivity utterly destroyed at the lowest temperatures measured. It wasn't a zero temperature, obviously, but it was down to millikelvin temperatures in a dilution refrigerator that superconductivity was destroyed. these studies continued. Here's another study 10 years later after that. And as far as I know, these are the only two papers in the literature. There was one in 2001, and there was one in 2011, and that's it. And what this one showed was, again, the same phenomenon. Here's superconductivity at a zero magnetic field, the destruction of superconductivity, and then it almost comes back. It didn't quite come all the way back to being a superconductor again, but at least it tried, but it was definitely driven all the way normal in this half flux quantum condition. And so this was also an example of destructive superconductivity at a half a flux quantum. Superconductivity was utterly destroyed. So that was a place where we entered into the problem, taking the nanowires that we'd been looking at in the previous talk, and now letting the stage, this cooled stage for the where the aluminum was being epitaxially deposited on the nanowire, and letting the stage rotate as well as being cooled during the deposition of the aluminum. So you end up with a nanowire. This is actually an electron micrograph that's chemically sensitive. We made it blue and green, that we did, but the contrast between those two is something that was the chemically sensitive scanning electron micrograph that shows the aluminum surrounding, this is an end-on scanning electron micrograph of the nanowire, now with superconducting aluminum grown epitaxially all around the outside of the system. So what happened? Well, interesting. Depending on the diameter of the wire, we saw either regular little Parkes physics, meaning a slight modulation of the superconducting order, or if the wire was skinnier, that the superconductivity would be completely destroyed. So we could go between regular little Parkes effect and destructive little Parkes effect just by changing the diameter of the nanowire. I have written on here theory, and it looks kind of like a joke, actually, that should actually be the theory curve. But what's amazing about the theory in this case is that it's extremely simple. It's so simple that there's only one free parameter in the whole theory. And you put in that one parameter, and it traces out those curves. It's ridiculous. So here's the theory, and it was what I showed you before with the ferromagnet. It's the theory itself is from the 1960s. Abrikosov-Gorkov formula for the transition temperature, now written in the language of this these so-called lobes of reentrant superconductivity. If I go back to this case, let's call this the 0th lobe, the first lobe, the second lobe. We can give the same designations up here. So this is 0, 1, 2. And the flux within that lobe in terms of the 0 lobe, 0 flux value. So that's a free parameter. That means this number right here, 1.4. That is a free parameter. That number you have to put in. Now what else? So there's that number is a free parameter. Everything else is not. If you look at all the other stuff, 1/2, that's okay. This is the critical temperature. This is self-consistent. You have to solve this. This is a digamma function, so you have to solve this self-consistently. And the only other thing going on in here is alpha. This is the so-called pair breaking parameter. And that pair breaking parameter doesn't have very much in it. It doesn't have anything in it that doesn't just come from measurements. It has a coherence length, but you can just take the coherence length from the parameters. You know the Fermi velocity, you know the mean free path because you know the resistance of the material, you know the critical temperature, and you can just get that number. You don't have to fit it. There's the diameter or the area of the wire. There's that one free parameter again. This is what lobe you're in. This is the flux within the lobe. That's the thickness of the shell. You just get that from the micrograph. And that's, again, the radius. So everything else is determined completely by just looking at the wire. And what you get are these curves, not only for the critical temperature, but also for the critical current. So it's a mean field theory, and this is a real amazing success of mean field theory. Again, I want to say, there's one free parameter here, TC00 and IS00. And everything else just comes out. Yeah?
Is there a slight skew in the critical current? Like are the lobes a bit tipped to the left? Or is it neat?
You mean this thing?
Well, all the lobes I would say are a bit tipped to the left.
All the, well, the left, the ones on the right are to the right.
Sorry, yeah.
Or maybe you're sitting in a weird place. From where I'm standing, they look pretty symmetrical.
Yeah, so symmetrical with regards to V is 0, but each individual lobe is not symmetrical along the x-axis. It's like
Oh, yeah, okay. There's a depinning and a repinning. So when you turn up the critical current, it goes normal. You're looking at the bottom one, right? Is this what you're looking at? Or are you looking at this guy? Sorry, just clarify your question.
it reminds me a bit of all the diode effect stuff you see. Like there's a skew and there's a different magnitude in the differential.
Oh, yeah, okay. So, okay, you're looking at the bottom graph. I'm just asking. You're looking at the bottom graph. Yeah, you're not looking at the top graph. You're looking at the bottom graph.
Yes.
Okay, fine. No, it's not diode effect. What it is, I mean, unless we're talking about something different. What I think you're seeing is the fact that this magnitude is different from that magnitude. Yeah, that's only because when you turn when you turn the critical current up, it's cold, and then it switches. But when you're coming back down, it's hot. And so it switches at a different point. What this means is that the data was taken going from bottom to top. If you take the data from top to bottom, it flips over. It's just because the retrapping current is slightly different than the detrapping because it's joule heated when you're flowing and it's colder when you're not flowing. But if you sweep the sweep the other direction, it flips around.
But there's also the skew, right? And if you have the skew plus this magnitude difference, it cannot just be heating.
What skew are you talking about?
The yellow parts.
Oh, you mean that there's some crap right there, but there isn't something on the other side?
It appears like the theory lines are indeed just, well, I don't know how to describe the shape, like a round trapezoid.
Yes, yes.
When you take the experimental data, it's almost like you take the rectangle and you rotate it inside.
Are you going to seriously give me shit about the disagreement between theory and experiment? That's the most amazing theory and experiment I've ever seen. Yeah, well, I mean, God bless you for solving that if you want to dedicate your career to figuring out why that green line is not right on the boundary of that other thing. But to me, that's so good it's a joke. I mean, it's a mean field theory. So, correct answer. Yeah. Okay. Yeah. Okay. So you can go a little bit farther. Maybe there's a little bit more skew here. This was doing a slightly more complicated experiment in which you start off with something which is regular little parks, non-destructive, and if you put a perpendicular magnetic field on, you can weaken superconductivity, and now it's Abrikosov-Gorkov with two pair breaking parameters, where we kind of hypothesized that if you just add one to the other, it was the simplest thing that we could think of, you would get, again, green theory. As you crossed from non-destructive to destructive, you can actually walk in between the two. And if you look at the title of the paper, this anomalous metallic phase, you could find at this crossover that thing right there is an anomalous metal. So anyway, all I want to say is that what's going on in the shell, this is all just shell physics so far. Now, it could be, to get back to your question, that the core is playing a role and that's responsible for the yellow being on one side but not on the other. Because the Abrikosov-Gorkov is just for the cylinder. It's not for the cylinder with a semiconductor in the middle of it. So it could be that. Anyway, this is just shell physics. This is just 4 wires on the shell finding out what the shell is doing. Yeah.
Sorry.
Yeah.
If the idea is to just look at the cylinder, what is then the reason that to keep the same thing in the middle? Because that's what you
Because now it's going to get cool. Okay. That was just to get, after lunch, just to get warmed up. Okay. Now I'm going to study the core. Now I'm going to study the core, treating the shell as boundary conditions. And what's going to be interesting is, if I go back to the previous, is that this is a different boundary condition than that. This is the boundary condition of a uniform superconductor proximatizing. Actually, I'll just go to the next picture because I think that it's the picture that I want to show. Yeah, that's the picture that I want to show. This is the boundary condition of a uniform superconductor proximatizing a core. And this is going to look like just good old boring proximity effect from a superconductor. This, on the other hand, is a more complicated boundary condition. This is a boundary condition with a twist. This is the boundary condition of a vortex, meaning that there's something non-trivial that's going to happen to the proximity effect because it doesn't, at the middle, it doesn't know what to do. It doesn't know how to proximatize if there's a twist in the wave function.
Sorry, just what is the arrow representing?
The phase of the superconductor.
Okay,
Yeah, so this is the phase of the superconductor as you go around in the circle. And within this first lobe, what happens is, take zero field. Then it's a uniform superconductor. But even if you apply an external magnetic field, as long as it'll generate currents until finally the current that it has to generate exceeds the critical current of the wire. Then you kill superconductivity all the way down to zero. It's a quantum phase transition. Then it says, oh, the heck with it. I've destroyed superconductivity. The gap is closed. It reopens, and it has allowed one flux quantum, one twist of the wave into the boundary. Then it destroys it again. Then it re-comes up. Now 2 twists of the wave function. It's like no, it's a right side. I mean, this is the boundary condition of a vortex is that the phase around the vortex winds by 2 pi as you go around the vortex. And now we can ask what happens to the core. The core is now our nanowire. So we've made a vortex, and we're imposing the boundary conditions where each lobe of the shell is a different boundary condition. This is a trivial boundary condition. This is a one-twist vortex. This is a twisting vortex going the other direction, etc. And now we do spectroscopy of the core by removing a little bit of the shell, putting a gate on it, and seeing what happens as you do tunneling into the core, just as if it was one of those nanowire experiments from my first talk, the Delft experiment or our experiments, whatever. You tunnel into the core in the presence of the shell, and you do spectroscopy as a function of bias, and this is what you get. When it's a trivial superconductor, if I take a cut at that black line, I get something that looks like this. There's actually a little dip right there because the induced gap is a tiny bit smaller than the gap of the aluminum, so there's actually a double, it's a small amount of difference between the induced gap and the gap of the aluminum itself, but not much, but boring. But in the first lobe, something interesting happens in the vortex. Now, this is a vortex boundary condition, and what you can see is a very clear peak in the conductance at 0 energy. We said to ourselves. That looks oddly reminiscent of a Majorana in a vortex. So we pressed on. And we looked at a number of other devices, and we saw that there were all kinds of states, but always in the first lobe, and sometimes in the third lobe if it had 3 lobes. There was, not always, but in some cases, I'll show you one where there wasn't, there was, in addition to these extra states, there was very frequently a state also at 0. These states, by the way, are the Caroli-de Gennes matricon states that live inside of a vortex, which I'll get back to in a second. But the presence of the 0 energy state is the one that I want to call your attention to. Some wires don't have anything in the first lobe. They're different diameter, different thickness of the shell, different gap. There's a variety of them, and so they don't always do it. More than half do, but sometimes they don't. But they always have these Caroli-de Gennes matricon states. So if you're interested in that particular problem, well, I'll tell you that in a second. But we went to our theory friends at the time, and we had that data with that 0 bias line, and we had this analogy to a vortex, and we were thinking, we made a vortex. It's like a BNC cable. It's like a vortex. And we went to our theory friends. I think the first conversation was with Roman and Karsten Flensburg. And we said, is it possible that the core of a vortex in one of these nanowires, these indium arsenide nanowires, has a Majorana? And they said no. Impossible.
Why?
They were wrong, that's why. No, why did they think it? Because they were just standing up, we were eating lunch, and we said, do you think that this seems reasonable? And they said, no, it doesn't seem reasonable. And then we said, well, here's the data, look at what we see. And they said, wow, okay, that's stimulating. And then they went back, and a week later, they came back and they said, do you know what we discovered? And I said, nothing. No, I said, we discovered that in fact, more or less in the region of the wire sizes that you're looking at, where the wire is approximately, remember the number I gave, 180 nanometers was the coherence length. When the wire is about the same size as the coherence length and the spin orbit is about the right size for indium arsenide, there is a region in which this quality factor is negative, meaning that this is a topological region. It wasn't a very gigantic part of parameter space, but in the region of the wires in which the diameter, it was more or less the same condition as the destructive regime. When the wire was small or comparable to the coherence length, you'd reach the destructive regime, and that was also the condition under which, with reasonable amounts of spin orbit coupling, you found this topological state. And that was a surprise to them. I think that they really came in, hoping to come back and say, ha, there's no such thing as that, but it was there, and they were themselves surprised. So let's play with this idea a little bit.
So may I ask
Yeah.
a very related question?
Sure, of course.
I don't know, it's just counterintuitive for me that like for a wide nanowire you have this flux periodicity, and I mean for me this is natural, but then when it shrinks then it disappears. So the slopes are not symmetrical.
No, it's the other way. When the wires get bigger, in diameter,
Yeah.
then the structure is more subtle. When the wire gets smaller, it goes all the way to zero.
Yeah, but it's also not periodic in flux anymore. So like the original little
What are you looking at?
Little parts.
little parts,
Okay, so do you want me to go back to like this picture? No?
even further.
This one. Let's say this one.
Yeah.
Yeah.
So you see that like for the first case, I mean it's periodic in flux.
Oh, I see what you're seeing. You're seeing that this is going down.
Yeah. So why?
Oh, it's going down. I'll tell you why it's going down. Because the shell is a finite thickness. Okay. Yeah. So it's a kind of a detail, and you see that it's actually in the theory curve. There's this second term which goes like the thickness of the shell, because then you're really putting field through the shell.
Now it makes sense.
Good.
Thanks.
Okay. Yeah.
So,
Yeah.
so if you look sort of on the boundary between the two regimes where you destroy the superconductivity,
Yeah.
you don't,
Yes.
do you have sort of a finite number of one-dimensional subbands? So if I look right in the middle,
Here. But this is on the shell still. Do you want me to look inside?
so if you showed one that was right at the critical point between where you were just about to destroy the superconductivity.
Yes.
So if you look at that one,
Right.
are there sort of a small number of
No, it's still a metal at that point. And what I mean by a metal is
many channels?
it's metallic aluminum at that point. This is still shell physics. So at that point, what's interesting about it is it becomes an anomalous metal. It's finite resistance all the way down to zero temperature. But it's still 100,000 channels because it's a number of atoms of aluminum. Yeah. But when you proximatize the core, then you can count modes in the core, and those are more like ones. So these Caroli-Dejean matricons are core physics, not shell physics. The shell is fully superconducting at this point.
So can I think of it whether it's an even or an odd number of subbands? It helps determine whether or not you get a Majorana mode?
No. You mean whether this? You mean the count of the Carolis? No. Okay, you want me to leave it for now? Okay, fine. Yeah. Okay, so here, this is maybe the clearest example of these Carolis interacting or coexisting with the zero energy state. And I just wanted to point out, so in recent, okay, we did something else that was not exactly theoretical physics in the same sense as the theoretical physics that most of you do. This was just straight up, extremely detailed numerical modeling of an indium arsenide wire with an aluminum shell and the electrostatics of a backgate and the gold wire and all of the band bending and really the kind of detailed things. This is what there's people at Microsoft for whom this is a real specialty, is to really simulate the device. And this was the theoretical data, including the existence of this topological region, comparing for this detailed numerical model with a real hexagon, with a real shell around it. That was their model in comparison to the experimental data. So I'll just point you to this reference. This is a rather new paper. This is just a month old. And this is really about drawing these analogies between the Caroli-de Gennes matricon states that live in real vortex cores of planar superconductors and this thing that lives in the cylinder, which is different because it mostly lives on the outside. It depends on the band. It depends on the band bending of the indium arsenide, and it's only an analogy because in the vortex core, the gap goes down as a function of distance. Here, the gap is 0 everywhere on the inside. Here, the bands are bent down because of the potential from band bending. So it's not exactly a Caroli-de Gennes matricon state that lives inside of here, but the important intuition that I want to give is that normally you think of the spacing or the spectrum of these vortex states as depending on the ratio. It's an energy scale, but the energy scale is delta squared over E Fermi. This is something that Charlie mentioned in his talk a couple of days ago. But here, E Fermi is comparable to the gap. So that's a ratio like 1. So the Caroli-de Gennes matricon states are on the scale of the superconducting gap itself, which is a distinct feature of the semiconductor, which is a low-density material, meaning that the Fermi energy is small compared to the gap. Now, this work goes on and studies how these things are skewed as a function of flux. And yes?
Just one last quick question.
Yeah, please. Turn the microphone on, though. Or maybe he has to turn it. Okay.
Is it just one picture before?
Yeah.
You show the right one and you say that...
Wait, no, this one. Yeah.
When you show that the superconducting pairing drops in the center, should there be some kind of a proximity effect that makes an effective gap towards the center of the sample?
Yeah. Okay. This is different than the pair wave function. These are bound states, like Bohr orbits, if you want to say. This is the spectrum of a confined one-dimensional channel multiplied by the fact that they're extended in the other direction. So in fact, they're not even discrete states. They're Van Hoff singularities because it's actually a one-dimensional system mod quantization condition from being stuck inside of a circle. That's different from the proximity effect. The proximity effect is about Andreev modes that live inside of this thing. These are circumferential bound states. I don't know if that answers the question. Okay, so, but there's an interesting thing which we see both in the experiment and in this theory. Let me just point out something in the experiment that you can see. It actually wasn't present in the numerics. You could say, boy, that numerics looks awfully good, but there's something definitely missing. So you remember I gave him a hard time for pointing out this very small discrepancy between the theory. But now let me point out a very small discrepancy, but it's one that I happen to think is interesting, which is that these are skewed. They're skewed to the right. And that skewing to the right is very interesting because what it tells you is that the flux needed to thread a Caroli-de Gennes matricon state is a larger flux. That's because it's at an inner diameter. So you can literally read the diameter of where these things live by the flux at which these things max out. Notice that the outermost one is symmetric and they move inward as you go to the higher Caroli-de Gennes matricon states. And that's just what's borne out in the numerics. This is from Pablo San Jose, Carlos Paya, and Elsa Prada, and they see similarly in their numerics when they depending on the model of their core, when they do tunneling from a normal to the superconducting core, they see that as the Caroli-de Gennes matricon states move inward, they also skew to higher field because of the radius that they're living at gets smaller. So it takes more flux to put 2 pi through a smaller thing than it does through a bigger thing. Okay, but as I think that we've learned, or at least I've said 50 times since I started, you can't say, aha, there, it's a zero bias peak, therefore it's a Majorana. That's not correct logic. So we go on and we try to do more things. And we learned in the last talk about one thing that we can do to try to learn something more, which is to make an NISIN dot and study its length dependence and look for the exponential of the Majoranas interacting with each other if those are in fact Majoranas. So here's how we did it in this experiment. We took one long wire. We got a little bit smarter, lithography-wise. We took one long wire and we made a little dot, a little longer dot, a medium-sized dot, bigger dot, bigger dot, bigger dot, each getting longer and longer and longer, all along the wire. And we measured Coulomb blockade. In this leftmost dot, we did it between that lead, and we used those gates to do the cutting, and this one to do the gating. And we measured Coulomb blockade of that little guy. And then we're going to move to the next guy, the next guy, the next guy, the next guy, and the next guy as they get longer and longer and longer. We'll do Coulomb blockade measurements and keep track of the peak spacings as we move to the right. So here's the smallest of the dots. Now, I've been looking at these pictures for a long time and you haven't. So let me go slow. At 0 magnetic field, the spacing of the Coulomb blockade as you change the gate voltage, that's marked EG, the gate voltage, is 2E periodic. That's the trivial boundary condition. It's good old boring proximity effect. It's a strong superconductor. The Coulomb blockade is 2E periodic. Then you destroy superconductivity. Now it's a metal dot. The dot's made out of metal. It's a normal state dot. The Coulomb blockade peaks are exactly 1E periodic. That's right here. Then you go into the first lobe, and they're kind of periodic, 1E, half the spacing, but not quite periodic. Then you go to the next destructive regime, then the next lobe, then the next destructive regime, then the next lobe. And each time you're in a lobe, the peak spacing is not quite periodic. It deviates from perfect periodicity, and you have a calibration. The calibration is when you're at the destructive regime, it's metal, and it is exactly periodic at that point. So I'm showing you some nonlinear functions over here so that you can see that it's still a discrete spectrum. But let's just pay attention to the same kind of measurement that I did before. Here's 2E, not quite periodic, but at each of the destructive regimes, absolutely perfectly periodic. Am I going too fast?
No.
It's okay? Okay, thank you. Well, now you know what to do. Now we have the data for how those interact with each other in the very, very short device. Yes?
How are you able to gate these if they're full shell? There should be a lot of screening, right?
One more time?
How are you able to gate these islands if they're full shell?
Oh, that's interesting. So Coulomb blockade is about the entire island. You don't have to move anything around inside of it. You're lifting the whole island up in the air relative to the leads which are grounded. So the leads are grounded, and you gate the thing electrostatically.
But I guess the chemical potential of the semiconductor itself doesn't change that much, right? Like, there's no field effect at work here.
No, there's no field, there's nothing penetrating to the inside of the wire, but the dot itself is going up in the air.
Yeah, okay, yeah.
Good?
Yeah, yeah. Sure.
Okay, good. I mean, you have to think about it a little bit, yeah. Yeah.
Yeah, just a related question to that. In order to get into a topological regime, let's say in the first lobe, should you have to, in principle, tune the chemical potential in the...
You can't.
But do you need to, like, let's say if you
No,
do a simulation...
this is what makes this not such a great experiment. You have to hunt for wires where it happens.
I see.
Okay, so we went through a lot of wires until we were in that little cusp of the, we look in hindsight that we must have been in that cusp. But there are many wires that aren't topological. And ended up on the cutting room floor, as they say. And then we found some that were about the right diameter. If they weren't destructive, if they just had this scalloped structure, they were never, maybe one was like a little bit scalloped, but still had a zero bias peak. But mostly, you needed to get into the destructive regime, which meant it had to be pretty small. And then those guys were destructive. Now, we didn't tune the spin-orbit coupling, obviously. But that's right, we didn't tune the density. We couldn't, yeah. Okay, but let me continue. Then, there's the next dot. There's the next dot. You just keep going. And now what happens is, let's look at the bigger, longer dot. 2E periodic, destructive regime, first lobe. There's no bump anymore. Now it's flat in the first lobe. Actually, if you're super careful, it's not exactly flat. As the wire gets longer and longer, these look like really evenly spaced Coulomb blockade peaks. But if you measure the distance between them, I mean, if you really kill yourself to fit over each of these Coulomb blockade peaks and find the centroid of each one of those fits, you'll see that there's still even-odd structure. And the great thing is that you have a calibration of the experiment because you can just go right over to the metal regime. When you're in the destructive regime, it damn well had better be periodic, 1E periodic. But if you go in the middle of the lobe, you see it's not, it looks like it is to your eye, but it's not periodic in spacing. So here's in the first lobe, you see you're outside the error bars for the even, odd. This is the difference between the even and odd spacings. And all the way to the very longest dot, if you're careful about measuring the spacing, it's not periodic. And you do have to be careful if you want to make a plot like this, which is, as a function of the length of the wire, how big was that overshoot in the first lobe? And what you see is it falls exponentially. Now, you might say, oh, lots of things fall exponentially, for God's sake. But you can compare it. You can try to fit various power laws. Here's a first power. If it was an Andreev bound state, you could get either a first power or a second power. It doesn't fit any power law that we can find. It fits an exponential. And so we can conclude that our data is incompatible with any kind of Andreev bound state living inside of this wire, because that would be a power law distribution and would only be compatible with an exponential falling off of two things living at the ends of this wire. Okay. So, are we done? Have we proved it? I hope none of you ever use that word again, except for math problems that you're working on. So, no, we haven't proved it. But what I can say is, I can't currently think of anything else it could be. Now, that could be reflecting my limited imagination. And we leave it to the whole world to think of other things that this could be. But the distance problem is extremely important, because whereas many things, as we saw in the last talk, can give a zero bias peak, finding an exponential fall off with distance is pretty hard to cook up something, especially when you bother to show that it's incompatible with a power law. Okay. We did all kinds of other things that with these kinds of full shell wires. I'm going to kind of speed up a little bit. There were a couple of papers that were published after this that said if you have a Majorana mode, you can tell because the zero energy states will make a pi phase shift except if there's a Majorana. And it says that you can rule out a Majorana if there's a pi phase shift. There was another theory paper about the same time that said almost the same conclusion, which is supercurrent reversals. That is a pi phase shift. If you could make an interferometer and see what the pi phase shift was in one of these wires, for odd occupancy of the quantum dot, a pi junction, in the trivial case, will not occur when there's Majoranas in the wire. That is, if you have an odd occupied quantum dot with Majoranas in the wire, you won't get a pi junction. Okay, it's a kind of a negative result, but it was a kind of a cute theory statement. So we did the thing that you would do, which was we took one of these nanowires and we put it inside of a squid. So here's the wire, here's one arm of the squid, here's the other arm of the squid. A squid is a superconducting quantum interference device. You can now thread, in addition to getting yourself in the first lobe by putting a magnetic field in this direction, you can also put flux in that direction and wind yourself through the phase so that you can examine the phase of the system. Now, I'm going to go a little bit fast here because I kind of want you to get the spirit of this experiment instead of studying it for a million years. And that is, you can measure if you have a quantum dot in one of the arms, whether that quantum dot is an even or an odd or an even state. And what you see in the 0th lobe is it doesn't really matter. There's a supercurrent that passes through that quantum dot. It doesn't care whether the occupancy is even, that's an E, odd for an O, or even for another E. But if you're in the first lobe, it makes a big difference. The first lobe has a giant feature in the odd state, but not in the even state. Similarly, if you turn up the magnetic field in the odd state, the 0 lobe has nothing, just like the even state. But the even state has nothing in the first lobe, but the odd state has a giant feature, which is some Kondo-like feature in which the 0 energy state in the first lobe is hybridizing with the spin of the odd quantum dot. I said that fast. I'm going to say the same sentence again. if there's a Majorana if the Majorana or a zero energy state in the leads, it can condo with an odd occupied quantum dot in the first lobe, but not the zeroth lobe. In the zeroth lobe, it's gapped on the leads. In the first lobe, it's got a zero energy state. That zero energy state can have a condo-like interaction with an odd occupied spinful dot. That's what this picture shows, and you can read from the title of the paper that it's a complicated physical system. But the point that I want to make is, in the zeroth lobe, just as predicted, it makes a pi junction. As you go to the odd state has opposite phase as a function of the perpendicular magnetic field. It's a little bit hard to see here because it's almost invisible on the screen. It's visible on my screen, but it's okay. Just take the cut, just look over here, and what you can see is that in the zero state, the even and odd are 90 degrees out of phase, 180 degrees out of phase. There's a maximum where there's a minimum. That's looking at the difference between this red cut and that blue cut. There's the red cut, there's the blue cut. And in the first lobe over here, the even and the odd are in phase. There's no pi junction. So it's a compatibility check. It doesn't prove anything, but it shows that similarly, because of this condo-like resonance, there's no pi junction in the first lobe. I was kind of playing around with those kinds of things. Now, the last subject I want to cover, and I don't know, video, do you know how much time I have? Okay, good. I just set up a boundary condition for looking at the induced state of proximity in this kind of a situation. And it reminded me, anyway, of a vortex. And we identified a zero bias peak with an exponential length dependence. Good enough evidence for me to call it a Majorana. Here's a different system in which you don't need to go all the way around. And what I said is that this is a kind of frustrated proximity effect, and it needn't be topological. Here, the boundary condition is locked in. Here, the boundary condition is adjustable, but it can be just as frustrated. This green thing in the middle, similarly, doesn't know what kind of proximity effect to have. It doesn't know whether to have a proximity effect whose phase agrees with that guy or whose phase agrees with that guy. So it's similarly frustrated. However, the right one has the advantage that you can put any phase difference you want. And when the phase difference is 0, it's unfrustrated. When the phase difference is pi, it's frustrated. When the phase difference is something else, it's less frustrated. Yeah. Yes?
So if you have, this is depending on magnetic field, this is the supercurrent.
No, the arrows indicate the phase of the superconducting order parameter. Yeah.
So there's no...
No current. If I'm in the middle, this is important to say, if I'm in the middle of the first lobe, then I have that condition on the phase with no current flowing.
Okay.
If I move to the left of the middle of the first lobe, I'll have a little bit of current going one way. If I move to the right of the middle, it'll go the other way. But in every case, that's just diamagnetism. It will preserve that phase of the order parameter throughout the first lobe. And then it'll be a double winding in the second lobe.
So don't you then get a P-wave superconductor in the
middle.
In the indium arsenide?
I think what I get in the middle, I don't know why you say
on the surface states, for the surface states.
This thing is extruded like a three-dimensional object coming out of the screen. So I don't know which surface you mean in that case.
The surface of the cylinder.
On the surface of the cylinder. You mean like this green, red, blue interface right there?
Yeah. I don't know, Charles.
Yes, well, I would say what I think I get is a topological superconductor. That was my claim.
If it was a topological insulator on the inside,
Yes.
then you would definitely have a Majorana mode.
Right. What I've made instead is
What you've done
is made a semiconductor and
you
yeah.
made it a good enough topological insulator in the same way that
Yeah.
Lucian and those guys made a topological insulator out of
Yes,
arsenic.
I think that's right. Okay. Did his answer make sense? If it were, let me just see if I can say what Charlie just said to show that I myself got it. If that were a topological insulator, then there would be very little doubt that this would have made a topological superconductor. It would have been a vortex core in a topological insulator straight out of the catalog. what I've done instead was, in the spirit of Lucian and Oreg, I've made something that by taking advantage of spin-orbit coupling, but orbital instead of Zeeman, breaking time reversal symmetry,
Exactly.
with orbital, not Zeeman,
Yes.
and proximity effect in a vortex pattern, I've gotten close enough that it found also a topological state.
Yeah, so that's what I was.
That's exactly what I was.
Yeah. Okay, good. But I want to drill down on the right side of this graph. Oh, yeah, sorry.
It's maybe a very basic question, but you have a single, like, you think you have a single Majorana inside this?
I think so.
And shouldn't they come in pairs?
Oh, sorry, there's one at the other end. I was only doing spectroscopy into one end.
Ah,
And I know they come in pairs, because when I made the thing short, I saw the interaction between the two. I saw when I made them very close together, they split. So I know there's another one. When I make them short, they interact with each other. And as they get far and farther away, the interaction falls off exponentially. That's now shown. You okay? You're making a face like you're not okay.
no, I'm
Okay.
I'm making a face.
Okay, fine. Okay, so I want to take this right side seriously. Now, what's kind of funny is that this paper has a kind of a heroic status in our field. This is the paper that introduced the famous Altland-Zernbauer classification of random matrices with particle hole symmetry that extended the Wigner-Dyson symmetry classes to include all of the particle hole symmetric, you know them, A1, BD1, D3, D, whatever those guys. But what's, for those of you who haven't actually read this paper, this is a figure from that paper. Believe it or not, this math paper has this device in the figure, in the paper. And I'll read to you from the text of the paper. In general, an excitation gap opens up in this normal region, and we arrive at the boring situation where the vicinity of the chemical potential is devoid of single particle states. That is, you get a trivial proximity effect in the normal region. However, by tuning the phase difference of the order parameter of the two superconductor regions to the special value pi, we can make the gap close. More generally, we expect quasi-particle excitations to exist right at the chemical potential whenever the phase shift incurred during Andreev reflection vanishes on average over the NS interface region. So it didn't just need to be two of them separated by phi. It could have been n of them, n superconductors, as long as the average over all n of them, the vector sum is back at the origin again. So 0 and pi is a good way to get the vector sum to go back to 0. But the vortex boundary condition is another way to get the vector sum to go back to 0. So each of them works. And I suspect that Charlie can picture what the next slide coming up was the extension of this to topological insulators, where it was established that with that same phase shift of pi across, that there was a topological transition when the material underneath was a topological insulator, producing Majoranas at the ends of this wire. So this is all the same kind of thinking of taking the vortex boundary condition that we did in the first part of the talk and replacing it with a simpler and important planar condition that has the same frustration, that the two have a vector sum of 0, the 0 and the pi. And that's sufficient in the case of the topological insulator to make a pi junction. Now, what happened in the meantime in the field is this epitaxial interface material got extended from one-dimensional nanowires to the two-dimensional plane. And I want to emphasize 2 is a lot more than 1. With a one-dimensional wire, it's very hard to think about loops and T's and branches and extended networks. But the entire semiconductor industry is based on planar structures. You can do anything you want when you have the plane, and you can do lithography and layering of materials. So the advent of the extension of this epitaxy to the two-dimensional material is a really monumental occurrence, and I think influences our path forward. So some direct versions without the topological insulator, but taking the same kind of two-dimensional electron gas material and now having this proximity effect was studied in a couple of labs here, this in Copenhagen, where if you now make what I'll call a planar Josephson junction, SNS Josephson junction, just like the topological insulator from Fu and Kane, that this system will produce Majoranas at the long end of this, of this junction, as if the junction was a wire. And now you could say, well, it's not really a wire, is it? Well, it sure is, because the boundary conditions are gapped. So it's got a gap on the left that normal electrons can't escape from, it's got a gap on the right that they can't escape from, and it has a pi phase shift that frustrates the proximity effect. So that's sufficient to produce Majoranas. Yes?
5 minutes for the question.
Holy smokes. Okay. Similar work from Bert Halperin. This is Addy Stern, and I think that if Addy is, I think he's not here yet, unfortunately, but whatever, he's going to continue this. Very similar analysis. Here, a phase difference of phi across the junction produces Majoranas in the presence of a magnetic field, and they emphasize the important point here, and the important point that they wanted to emphasize was that just as you might expect, that the magnetic field that you need when these two have a phase that's the same, which is now, this is now the conventional phase that drives you with Zeeman energy into the topological mode, here is much lowered, and even when you include disorder, there's a great reduction, because the gap is collapsed, of the magnetic field that you need, or the Zeeman energy that you need relative to the gap, in order to produce the Majorana topological state. So that was a great generosity from having this phase shift across the system. There was another important generosity, which I'll just flash given the time, and this was again from Addy Stern, and he may want to talk about this, which is the fact that whereas one is incredibly sensitive to disorder that takes you in and out of the topological state in these long wires, in fact, in this SNS geometry, a little bit of disorder helps. So the system actually benefits from the fact that you scatter between modes, and if you see that this tau, this scattering time, as the scattering rate, which means 1 over t, as the scattering rate becomes longer, there's this upward trend, and the system gets actually, what happens is that the coherence length, in this case, gets longer, and so I don't really have time to explain it well, but as you get more and more disorder, as the rate goes up, the coherence length extends, and you get more and more Majoranas extending into the bulk. So the system is actually improved by moderate disorder. This was enough for us to be motivated to try to build it. So we did. It was a complicated problem to get an SNS junction that was gateable, and also that you should be able to detect Majoranas. So it was a lot of, you had to build a point contact at the end of an SNS junction, and you had to bias it, and we had a second junction so that you could either bias it with current or bias it with flux. And it was a pretty tour de force of lithography. At the same time, in parallel, in Amir Yacobi's lab, they were doing very similar experiments using, in this case, topological insulator material, again with flux and looking at the end of the state. And they saw zero bias peaks, as I'll get to. But let me, before telling you about this, just show you that the numerics for the actual device showed this topological transition, which had these very interesting features. I see you standing up, Vidya. Which is the system is trivial, there's a band crossing, it splits open again, but where the crossing occurs moves from being at pi to being at 0 as the Zeeman energy increases, and that was kind of the signature that we were looking for. Here's what the experimental data looks like, and I apologize for going so fast at the end here. This is as a function of perpendicular magnetic field that sets the phase across this junction. Here's 0, pi, 2 pi, etc. And you can see at 0 Zeeman field, nothing. It's just an SNS junction. So it's SNS, you put flux through it, and it winds through the phases, and that's what the gap measured spectroscopically using that quantum point contact shows. Now you start to put on some Zeeman field, 1/4 of a Tesla, 1/2 a Tesla, 0.6 Tesla. And just as expected, first starting at pi, then extending all throughout the region, and then finally, only absent at pi, just as predicted, was a zero bias feature that appeared. So in the interest of time, I want to, I'll move on and show you what happened after that, which was a second generation of experiments. This just out in January in the archive. The situation has gotten even more complicated. We wanted to be able to probe Majoranas at the two ends. It's gotten to be ridiculously sophisticated lithography at this point so that you can have an internal contact so that you can measure the left end and the right end. And these paddles have gotten larger because they have to be large compared to the coherence length. Now, with that increase in size, you now have, as predicted, a kind of greater resolution on the spectrum. And now what you can see is much more than you could see before. A superconducting gap at zero magnetic field, the gap closes, the gap reopens, and when it reopens, there's a zero bias peak. And it happens at both ends at the same time. Here's a kind of a zoom in so that you can measure that it's kind of a 250 or 30 microvolt topological gap when the thing reopens, and a zero bias peak that only appears when this thing reopens. Here's the numerics for the same problem, and you can see that there's a, in this region, there's about a quarter of a Tesla, there's a Majorana state that appears. Same thing as a function of flux. Here's the numerics, here's the experiment. As you turn up the in-plane magnetic field, the zero bias peak shows through all patterns. I'm going to end quickly. There's a lot of stuff that I wanted to show you. The theory says that it's actually not topological throughout the space. These red regions are where it's topological, so you have to kind of go find them. When you look at the right region, you find the zero bias peak. When you look in the wrong regions, you don't, and that's about the same amount of time as you see in the experiment. And I wish I had enough time to tell you all about this nonlinear transport, which I don't, non-local transport. I'm going to end instead by setting up Addy for his talk in the following way. Imagine that you actually believed in this stuff. Imagine that you thought, wow, that was a good idea. This is more robust to disorder because it's grounded superconductors, and the disorder helps scatter you between the two sides. And it actually kind of works. Like, the gap closes, it reopens, there's a zero bias peak. Kind of works. What do you do next? That's now the hard question. And this is, the hard part of doing these experiments. You got something to work, and now you have to say, what do I do next? Well, imagine you want to braid with these things. You have to be able to move the Majoranas around. So here's how Addy says we should do it. I don't know whether we're going to do it this way or not. If you put in a large magnetic field, you'll actually get nodes in the wave function in the perpendicular direction. Before I put on a perpendicular magnetic field, but it was only enough to change the phase, to give me that pi or the 2 pi, etc. Now I want to put in flux on the scale of the junction itself. I want to actually put flux through the junction part. And if I do that, as I get near pi or 2 pi of junctions, I get nodes of this wave function. And what that lets me do is place Majoranas throughout this location inside the junction. And if I can do that, I can move them around. Okay, now, I will tell you, this is going to be hard. This is going to be hard. It's not hard to put the flux through. We've already done that, and it does work. The hard part's going to be braiding. And I guess what we should think is, I feel actually like this is easier than, continued hope with the long wires. Because I think with the long wires, it took us years and years and years before we got to a place where, something made a zero bias peak. And we never got to the place where we had an evident, I have to go back to where the data was, where we had an evident gap closing, reopening, and a zero bias peak. That happened more or less out of the box, and it happened at both ends of the device. So, sometimes it was. It wasn't. Again, the topological space isn't that big anyway, so you had to tune for it. But when you tune for it, it kind of agreed with theory. Like, 10, 20% of the time, you'd find a region where it would do that, which is what's expected. But to me, this actually feels a little more optimistic because it kind of works. And so if you ask, is it going to be hard to move those Majoranids? Yeah, it's going to be hard, but I think it's worth doing. So that's probably a direction we're going. I think these SNSs feel more like they scale. You can put multiple ones on the same chip, and they work. With that, I'm going to stop. I hope you've gotten a little bit of the spirit of what it means to try to do these experiments, and that you'll never use the word prove again. Thank you. No time.
Sort of round thing, but if you have a burning question, okay, ask me one.
All the questions are good.
Assuming you did the braiding, which is hard, how can you see that it worked? Like, how can you?
It's a good question. I'm going to try to give you a quick answer. Braiding, you know, there's a -1 that shows up. It's this branch cut, right? So you do the thing and there's a -1 that shows up. But if you do it twice, it comes back to a +1. So I think that the key to observing braiding is to double braid. This was something that was emphasized in a paper that we had with Jason, which is you have to do things so that, you know, if something diminishes after you do it once, but it comes back if you do it twice, that's a little harder to understand than if it just diminishes when you do it once. So if something picked up a -1 and it changed, it wouldn't be enough. But if you can restore it by braiding a second time, then I think you get greater confidence in it. But again, it's just greater confidence.
But if there would be no minus sign, then doing it twice is also you get the same.
That's right, you get this. That's right. So you go, that's another good control experiment. You go to some regime where it shouldn't do it at all. Remember that we can easily tune by going to zero parallel field. You go out of the topological region. It should not work. It shouldn't go down then back up. It should never go down at all. So there should be enough checks that any reasonable person would say, it seems to pass all these checks. Still doesn't prove it, but it's a lot of checks.
Okay, I think we'll leave other questions for breaks. Charlie, that was amazing data. Thank you very much.
Thank you.